So let's use this balance to solve the same example as before. So we're looking at this reaction, 2A goes to B. It's in an isothermal, this time constant volume batch reactor. We know the rate expression. Here's the rate constant. We know that value. And we know the initial concentration of A. And we want to determine the batch time needed to achieve a concentration of 0.1 molar. So in this case, what are we going to solve for? So in the CSTR example, we solved for a volume needed to do that. In the case of the batch, we're going to solve for a batch time, so a time or reaction time. So what time is needed? How long do I need to run this batch for in order to get this concentration? So the rate of reaction in the batch reactor, this is going to be, so in the CSTR, the rate of reaction was constant. So we have one uniform concentration in the CSTR, and it doesn't depend on time. In the batch reactor, the concentration of the different species changes with time. So for example, A, the reactant, starts off at a high concentration and the concentration decreases with time. In contrast, the product, B, starts out at a low concentration and that concentration increases with time. So the rate of reaction in a batch reactor depends on time. In fact, let's say it's a function of time because it's a function of concentration. So it's not constant. So let's see how this works. So I have dCA dt equals RA. A is being net consumed, so the rate of A is going to be equal to negative K CA squared. And this makes sense. So this is a time derivative. So this tells me how the concentration of A is changing with time. A is a reactant, so the concentration should be getting smaller with time. So that means that the derivative, this derivative, should be negative. So the rate of change of A, of the concentration of A, is negative. And so we put this negative sign here. That makes logical sense with what we would expect for our balance. So this goes back to this accounting issue and ensuring that the way we use negative signs and the way we enter the rate expression into our balance equation properly accounts for whether the component that we're interested in is being generated or consumed. In this case, it's being consumed, so we want to have a negative rate. So now let's combine these. So we have dCA dt is equal to minus kCA squared. And so to solve this, I'm basically going to do separation of variables. So I'm going to say dCA over CA squared is equal to negative K dt. And then I'm going to integrate. So on this side, my limits of integration, I start out at CA naught, and then I go to CA. And then here, that was a bad integral sign. I go from 0 to t. So if I integrate this is basically CA to the minus 2. So the integral of that should be minus CA to the minus 1. So, and then if I take the fact that this is a definite integral, I can say minus 1 divided by 0.1 plus 1 divided by 2 is equal to minus KT. So I can say then that T is equal to all of this divided by K. or minus K. And I had an answer for this that I don't remember, so give me a second to look. So if I solve for this, I get 317 seconds. So that's how long the batch would have to be carried out, or the batch reaction would have to be carried out in order to reduce the concentration of A from 2 molar to 0.1 molar.